Okay. Good morning, still morning. Thank you for attending this webinar. As it says on the screen, if you've got questions, use the question tab. I'm more than happy to take them as we go through. Got quite a bit of turf to cover, but we should be able to do it in an hour. And by all means, there's my email. If I can answer questions after this, please send me emails. And link. If you haven't got the PDF, you'll probably want to pull it down. It's got some good information in it. So, good morning, one and all. And again, welcome. So let's dive right in. So we got prompted, I should say one of my coworkers got prompted by a couple of people about, dump rating is a lost art. So this may be the first, I don't know, we'll see. Simple information about how to look at dumps. In this case, I just picked on CICS only because I have things well prepared as far as that goes. So, all right. For all you folks who may not be familiar with hex, here's a slide that will kind of things, but I do want to kind of highlight at least a little part of this. When we're looking at a CICS transaction dump, okay, and to a large degree the system dumps, basic format. So we're going to have the offset over on the left-hand side. Assuming you've got, you're looking at like a printout, from in SDSF or something like that, we're going to get hex 32 bytes worth of dump area. And I kind of put the little headers up there, right? That's done in forward or full word chunks. So 04 or 00048 Charlie 101418 Charlie. Okay, so to help compute the offsets. So that's the hex. We then get the character representation in between the asterisks. Sometimes you'll see things you recognize. Most times you'll see a bunch of periods, simply because there's not printable characters. And then, of course, if we're talking about addresses, they'll be over here on the far right. Okay, so essentially that's the basic format of the dump we're looking at. But you're going to see that a CICS transaction dump is highly formatted. So there's many times we don't have to get down to that kind of detail, if you will. Okay, so marching on. Next few slides, what I've got, and again, if you got the PDF, you're in great shape, is I'm highlighting the sections of the dump. I'm just pulling different parts and kind of give you a heads up, if you will, of what's in each section. Okay, the little octagons on the right-hand side correspond to the points in the text. So you can kind of separate out, and I just give you a few highlights, if you will, about what's there. So right off the bat, why did I go away? Well, I program checked. Of course, we know the transaction, okay? And we know the date and time when it's occurred. Basic information. Of course, we also know the program now. This RIDS field is the actual program at which point the Abend occurred. Now, we may get led astray as we go walking through a dump, but this is the point or the program that the CICS believes the Abend occurred in. And of course, my CICS level 700 just basically happens to be 5.3. Okay. So section Baker. If I've got a program checked, then we have PSW. The important full words in the PSW are the two right there. And again, we'll get a bit more about that, I think, coming up on another slide. The other kind of important thing is the registers, right, at the point of the Abend, if you will. And again, we'll point out some key information about what we're going to find in the registers. I do want you folks to notice, if you haven't seen a transaction dump or even a system dump for a long time, IBM is, in many cases in CICS, started to already plan or set up, if you will, 64-bit data areas. Even though our current COBOL compilers don't support 64-bit, many places in CICS they've already provided for that 8-byte address. Okay, as you can see here, the registers are all shown in 64-bit, even though the addressing mode, as you can see it, is 31. The next little section that we would see is section C. And of course, a couple key pieces of information. We are user mode. Exec key 9 says that the application is running in user mode, which is as it should. And then the register is at the last command because this register 14 at times can help me out, as you'll see. Okay, so the next thing we get, section D of a dump, is this lovely interpretation of this task control area. Okay, so we don't have to get into the bits and bytes. We don't have to pull out the IBM data area manual, none of that kind of nonsense. Most everything you need to know about the transaction is here. And in fact, a couple of very important things. Initial program was A, current program is C. Tells you got more than one program involved. We can also see things like the terminal ID if you care, runaway limit of 1,000, which is 1,000 milliseconds, D timeout, S purge being coded, right? I do have a TWA, and that actually shows down here in F. A lot of people today are not using transaction work areas. Well, I kind of threw one in just so it shows up in the dump. Okay, so it will clearly show, you can see the length, 64 bytes. So a whole bunch of information, and I don't have to go digging into the bits and bytes. It's nice and neatly formatted. Section echo that you see, TCA, task control area, this is part of what's referred to as the AP domain. And the data areas within an AP domain are all documented in the CICS data areas. So you could find the layout of this. What you'll find, even though the shows you what's referred to as the TCA, task control area, and the system TCA, the task control area, system area, it's really one big data area. Goes back to the old days of CICS when there were two separate pieces of storage, all one now. Okay, so again, just basic format for now. Area G. Command level, we have what's referred to as the Execute Interface Block, or EIB. In reality, there are two. Section H, as in hotel, this is the one your applications are testing, the EIB. Section G, as in golf, this is the one that the system's kind of using internally to help process your commands. At times, it can be useful, depends upon the situation we're looking at, okay? And again, we'll get into a little bit more of that. Section I, as in India, please ignore. Table Manager Lock Block has to do with supporting searching the in-memory tables on behalf of your application when you access files, things like that. Not a lot of things I really care about looking at there. So we can kind of ignore that one. Section J. So I have very few lines here. You're going to kill a small tree in the real world. In CICS, there's a domain called the kernel. The kernel is like the heart or the traffic cop, if you will, of CICS. Maintains information about all the domains, everything going on in the CICS region. Well, just in case you wanted to send IBM a transaction dump because that's all you have, they put these data areas, what's referred to as a kernel stack, and you'll see auto stack data areas. They put these things in the dump, transaction dump, just in case you send them a transaction dump, they got a bit more information that would normally go beyond the transaction. If you're a developer, please ignore it. If you're a systems person online and you're working with developers, please tell them to ignore it. It will be quite a few pages of a typical transaction dump. Not a small thing, but of primary use to IBM and not us. Most of the data areas are not documented. Section K, as in king. So the common system area and the optional features list have been around in CICS for ever since its inception back in 1969. It is documented because it's part of the AP domain. Very little useful information anymore. Okay, as IBM starts to pull things out and make these separate domains, this data area becomes less and less useful. I really don't go to it myself a lot. Big reason I'm here is if you have a common work area defined in your CICS region, this is the point or the place in the dump where you will find that particular piece of information. And of course, the common work area is for all of your applications to use, and the information there could be important to your applications. Section L, again, very small bit of information compared to what you're going to find in the transaction dump, and that's trace. And I've done a webinar in the past on using trace to help profile and analyze applications. Trace is my friend. If I want to really seriously debug an application or solve storage violations, profile an application of what it's doing, trace is my friend. I can tell you anything you ever wanted to know about your applications through trace. In that presentation, and it may still be on our webinar website, I actually describe what trace settings and things like that, so that would be a worthwhile trip. I don't need all of trace. That's about 20% overhead. The way I tweak it myself, it ends up to be around 6% overhead, maybe 5%, somewhere in that range. So I tweak a bit of trace out. Keep the good stuff in. So trace in general. Abbreviated trace, full trace for the same entry. Notice it's entry number 1. Hundreds of pages in a typical dump. Tons and tons of data. A lot depends upon an option of how much trace you're going to allow the system to capture. Okay, so moving on. Section M, Storage Manager Transaction Area. Now, this is a data area germane to CICS managing storage of your applications and of its own internal domains. Data area is not documented. What is there is kind of easy to figure out, but not a real reason for you to do that. What it does is tell us all the pieces of storage that we're going to find labeled as transaction storage in section N. Now, again, only a limited amount of lines here. Again, we will kill probably a small tree at this point. So as a consequence, the data areas are going to be in a form of, they're going to show us the CICS 24 first. If the first entry in this section is, as mine was, CICS 31, there is no below the line storage, which is a good thing with today's applications. It would be presented as CICS 24, user 24, CICS 31 as you see on the screen, and then user 31. So all the data areas that your application owns, your task owns, will be listed here with those headers and all shown separately. So if you needed to get into a particular data area, okay, and again, Displacements on the left, 32 bytes worth of data in hex, the character display the same, and then the address on the right. So you could always find the addresses and so on. Right? Some of the data areas will be records, screen images, however you process, especially if your applications are doing set commands. This happens to be a data area called TACB, associated with the Abend. Okay, and as you can see, there's information like I showed you on the first page. The Abend type, ASRA, and the program, if you will. And that is documented. So we'll see more about that in a little bit here. Next section, O as in Oscar. Table, internal control table. If your region that you're running in is a TOR, you'll have a real terminal. If your region is an AOR, it'll be a session entry, but it looks like a terminal entry because that's how they represent them. BMS extension, TCT sign-on extension, all that is documented. Main reason I'm here is right there, terminal storage. If I need to look at data areas that have come into my program through terminal, that's where I'm going to find them. Okay. If I got to look for possible storage violation in terminal control data, that's where I'm going to find it. Section P. Now, Section P is really a character interpretation of Section Q. In Section Q, I will find printed out the load modules in memory of my programs that are involved. Okay? So basically, I can ignore looking at the program code. Unless you can read machine language, unless you know quite a bit about assembler, looking at the programs in memory is not going to do you much good. Right? It's the load modules, right? However, the bit of information in Section P is quite useful to us. So in applications, we can do command level links. We can do XCTLs. This is going to show us, in a sense, the path our applications has taken. If you'll notice, kind of like a push-down stack. So this is level 1 of 2. Program was Z00 alpha, right? The invoking program was CICS. So we now know that was the initial program as part of our task. You'll notice it's got the load and entry points, which could be useful, as you'll see later on. Okay. It is a mode 31, and we can see an awful lot more information. It is thread safe, as it should be. Okay. However, when we look at the current level, we see that program Z00 Charlie. Okay, in level 2. Notice invoking program, however. B. So how do I use these data areas? Well, I can say quite simply, CICS linked to A, because that's how CICS gets to your first program. It does a command level link. Program A linked to B. It's at level 2. However, program B XCTL'd to C, and B is now out of the question. So this data area can tell me quite a bit about what my transaction's gone through. Once again, load points, entry points for my program, and of course it is thread safe, as it should be. Okay? So we're going to get into the data areas after the programs. Section R, as in Romeo. These data areas, please ignore them. It's essentially the data areas that supported that little summary, character-based summary I just went through. No reason to get here. They are also not documented. Okay? Section S, as in Sam, is where it's going to show me some kind of important information. If your programs are using COM areas, you will see that in the program areas. If your programs are using channels and containers, as mine are, at section S, I'm showing you, we will show, or it will show you your channels and containers. Now, the unfortunate thing is it shows it for, well, I shouldn't say that. It may be fortunate. In my case, it's unfortunate. It's going to show me for both programs. Well, if you kind of look, same channel name, same as channel, same container name, same as container. Had I passed a different channel and a different set of containers from A to B to C, it would have been different. But in my case, I'm just using a single channel, single container. All right. Principal reason was just to show you where they're going to show up in the dump. Section T as in Tango is nothing more than a layout, or as a data area called load list elements, and then the potential elements themselves. The only thing that's going to appear here is, in a sense, what is kind of like program entries that have been loaded on behalf of your task. Okay? And then last but not least, section U is a module index. It'll be a few pages long, and essentially it's just a listing by load point address of all the modules in CICS. You'll see a bunch of DFHs. You'll eventually see your programs. Okay, and that's in case you got an address and you want to find out what program it's in. You can kind of look in this area and find out. Most of the time, it's going to be in the programs within the transaction dump, your application. Okay, so working with Abend. Quick page of information. So here are quite a few of the common Abend codes. ASRA, what we're going to look at, program check. And the most common ones are OC4, OC7, OC Baker. The OC4 is the protection exceptions. Typically an address gone bad. OC7, data exception, you got some bad data. Sorry. OCB, you're trying to divide by 0. AICA, runaway task. All those will be solved in a similar fashion to the way we're going to see it here. Okay. AEZD, Able Easy X-Ray Z, or Z Delta rather, sorry. User program mode invoked in a CSS task. Sorry folks, I did it to you. I defined your task as CSS mode and you're trying to run user mode programs and oops, they don't work. ASRB, applications caused invocation of ZOS Abend routine. Essentially, something in your application has caused CICS to pass data to something like, let's say, VSAM, and VSAM doesn't like the address or doesn't like what's going on, and it abends, if you will, on your behalf. Okay. Most likely cause is you've got some kind of a storage violation that your application typically has caused. AEXZ, application is victim of a storage violation. Well, maybe. That's another whole webinar or another whole story, how to solve storage violations. But when you see them, you don't know if you're the victim or the perpetrator. AEY Delta, command protection event. You can turn, as your administrator, can turn a little thing that says, okay, every time an application does a command, check storage areas to see if they're violated. If one is violated, I get this event. It's a transaction. ADXX, events related to the DB2 interface in CICS. AEXX, you do not have proper error handling, right, for commands, and they're very unique. AFXX, something related to a file control request. Again, your application is clobbered a data area that file control needs, typically. Far more. But these are the ones that are, I have seen through my travels of CICS in the past 20 years, commonly being done or happening to folks, okay? If you are running CICS mode, ASRA becomes AKEA, ASRB becomes AKEB, and AICA becomes AKCA, or AKEC. If I'm looking at the AEXX events, the EIB is my friend, EIBFN is function code, And again, the data area is documented, but that happens to be at +1 Baker. The response and response to are very useful. EIBDS contains the last file accessed, and EIB resource will be the name of the last resource other than a file. So, bit of information, right? Okay. So, getting a little deeper. So that PSW. So the ones I highlighted was this next sequential instruction at offset 4 into the PSW. Forward has a thing. Again, next sequential instruction after the one abends. In +8, it actually is 2 half words. We have the instruction length and then the exception code. Okay? So the exception code, if I was dealing with an, 0 Charlie 7, would be 0007, right? The instruction length is germane because if I wanted to look at the dump, or I wanted to get the real Abend address of the real instruction, take the next sequential instruction address minus the instruction length, and that gives me the address of the failing instruction. Okay? That's our starting point for dealing with the PSW. Okay. Now, we've got basically an address, right? The NSI. We back up to the failing instruction. Okay? If you can read hex or assembler, delta 2 is a move. And of course, the basic move instruction, base and displacement, base and displacement. So I'm moving from data located at register 2 plus 34 alpha to register the address in register 8 plus 0. Sounds perfectly normal. Well, to find that instruction in a COBOL program, we need the entry point. Now, I show you a little stub program. So you got the load point, little stub, and the entry point. If you kind of go back to where I was showing you that information, key information about the program levels, and get the load and entry point, what you're going to find out is they're both the same. And that's because the stub is really attacked on the end. I mean, some prior releases to version 5, the stub was on the front. It seems that within version 5 CICS, the stub is on the end. So load and entry point become the same thing. Doesn't really matter. The way you find it in a COBOL program, if you've got an actual compile list, as we're going to show you, you take the entry point, you subtract that from the failing instruction, and you get the offset into the program. At which point, and again, I'm going to show you this, you can get to the what's called hex block location, right? Hex, it's LOC, right? Lock or loc, whatever you want to say, and find that closest address, right? That's not above, okay? Or pardon me, and back up to the previous instruction, I should say, and then find the line of COBOL code. In my case, I said move WS item description to LS item description. Okay, kind of goes with what I showed you, right? D2 is a move statement. So, kind of put it together here. So, again, these areas are kind of bolded. Okay. So, ASRA, Abend, transactions THM3. Please notice that it's THM PGMC is my program. 690 for a Kixer level, so that's 5.2. Okay. My PSW address, we'll talk a bit about that address in a second, right? It's over here in the note on the side. The instruction is 6 bytes long, and it's a 0007, so it's an OC7. Okay. Now, I said the address or the registers at the Abend are useful. Now, we are talking Enterprise COBOL version 4 and earlier here. And the reason I say that is because I'm looking at something called a TGT. With Enterprise COBOL version 5, IBM is now building what's called program objects. And oh, by the way, you don't have a TGT anymore. But please bear with me, you will see some other things. So register 9 is the address to the TGT. Register 13 is the address to something called a dynamic storage area. And again, we'll see a bit more about those. If I take the registers of the last command and I look at register 14, that's the address of the last command. Now, in my case, you'll notice that the register 14 address and the Abend address are two different things. And that's good news, because that gives me two different points in my program to look at. So if I'm trying to resolve an application Abend, that's a good thing. I got the place where it failed, plus I got the place of the last command. And that gives me a section of code or a spot of code to look at, right, in the compile. So picking up those addresses. The real next sequential instruction is 274.269 echo echo. The alpha bit, or if you will, or the alpha in the first character is a hex 80 bit. That has to be ignored when you're looking at addresses, simply because that just says we're running 31-bit mode. Minus my 6 for the instruction length, and we end up with an address of 274.269 echo 8. I subtract out the entry point, right, 57 Baker 0, and I end up with an offset for my program, 1238. Okay? Similar thing with the register 14 address. Forget that hex 80 bit. So there's the actual address, right, ending in 693 alpha. Subtract the same load or entry point again, right, 57 Baker 0, and I end up with 118 alpha. So at that point, right, I've got two different spots to look at and potentially find out what's going on. Again, back to that program section, this is where I've got the load and entry points, right? So there's the entry point for the program that I was showing you. Of course, it is 31 and it is program C. And again, we came there from program B. So it is quite useful information. Now, in trace, and now bear with me. In trace, we're going to find exception trace entries, even if all of trace is turned off as far as you think. We're going to find exception trace entries. And as a consequence, they're going to show up, and in this case, they're going to represent the events. Okay? Well, there are going to be several of them. Not sure why IBM puts out so many exception trace entries, but there's little tidbits of information in them that can be useful, such as the first exception trace entry tells me the program name again, PGMC, THM PGMC, okay? The data areas, it lays out what these things are. The first data area is parameter list, not totally documented. The second data area here is what's referred to as kernel error data, KE error, right, data. That's a data area that's basically the kernel captures. It's the kernel catches every Abend and saves minimal information about it, okay? So the kernel, right, has captured this off, and it is documented, so you can pull it apart. But essentially, it's PSW, registers, program, a few other things about the Abend. Second exception trace entry, we see data area 1 is the same thing. And then finally, this other exception trace entry, and this, by the way, system recovery program, we see our program again, but now we see it actually calculate offset, 123 alpha. Now that's for the next sequential instruction, as it says. And if I subtracted 6, I'd end up with a 1238. Okay? So I can get some bits and pieces from trace if need be. Okay, hold on a second, please. Sorry. Okay, so working with Enterprise COBOL 4. And a lot of people are still using COBOL 4. Unfortunately, it's going to go out of service here pretty soon. Okay, so I'm looking at that hex loc in my compile list. We've got to have a good compile list, folks. And I find an address, and here's the 1244, right? Which is not which is higher than. But here's the 1, 2, 3, 4, statement number 136, and it's an add. So that's the 1238 address. So when I look up line number 136, I find out it's an add 1 to WS value. Okay. Now, the listing, I can find WS value, and I find out it's basically, defined as a field. And I'm adding 1 to it. I don't show you the whole thing there. But if I look at the add statement, I know the problem has got to be WS value. Why? Because 1's a literal. Literal can't be bad. COBOL doesn't generate a bad literal. So WS value's got to have the thing. Now, I mean, it's obvious I put forced bad data. What I wanted to show you, though, is if I wanted to find that in a dump, I would have to use these things out here. Base locator working storage, BLW. Which one? 1. Okay, starts with 0, but this is base locator 1, plus Charlie Echo 8. And if I get there in the dump, right, once I find the address that's in BLW 1, and get there, it's a 4-byte packed field. So if need be, I can go find that particular field in the dump. It will be in those transaction storage areas I showed you, somewhere. And there could be a lot to look at. But I've got addresses. I'll get addresses, I should say. So in the compile list, these are labeled. I just kind of gave you little data areas so you can kind of visually see these things. And you will see those in a second. The dynamic storage area, pointed to by register 13, has a standard save area in the front, right? Standard register save area, 14 through 12. Plus 5 Charlie, and again, please remember we're talking about Enterprise COBOL 4. Plus 5 Charlie, we get the address of the TGT, okay? So, could be useful to find another way, but the best way to find it if you're dealing with COBOL 4 is, and earlier I should say, register 9. Now, the TGT is also documented in the COBOL compile list. Couple highlights, plus 100 program entry point, plus 114 address of working storage, could be useful. In this variable portion, and you really have to look at the TGT list, and that's coming up, we'll find the offsets in the TGT, or we'll be able to find the TGT in the dump, register 9, and we'll find the offsets to the BLWs. And then we can find BLW1. There's also base locator linkage if you've got items in the linkage section. And again, you'll see something brief on how to look at that. Okay? So here's the COBOL compile list that shows the DSA. And again, I've just bolded some key things for you. So the register save area is there, the address of TGT at plus 5 Charlie, plus something called the common anchor area, which is the master control block, if you will, for LE associated with your transaction, right? The LE data areas are kind of documented. So, and again, the rest of the DSA. Finally, to the TGT. So, if you're looking in the dump, you got the register 9 address, and you're looking in a dump, the way you know you're looking at the correct spot is at plus 48 from the start of the TGT. So if you get the address add 48, you'll find the identifier, and it'll contain 3 TGT. And I just looked at my text and I said I'd offset 84 in the text. Fingers must have flipped. It's actually at plus 48. I just noticed that. Okay? Or I'm sorry, I'm looking at something different. Never mind. Never mind. Okay, I actually highlighted that. It's the hex 84. I'm sorry. Guess I shouldn't look at my own text. Length of TGT. How big is it? Okay. Not going to get into all the other stuff. But we can find the start of the COBOL program. Of course, we'll see it clearly in dump. We can find the working storage address at 114. Again, could be quite useful. And then notice this variable portion, 12 Charlie, is the base locators for working storage. Now, they're full words each, so 12 Charlie would be BLW0, 130 will be BLW1. And then right away after that, the base locators linkage, BLLs, starting at 134. Now, those are going to depend upon how many O1s you have in your linkage section, okay? But they're going to be laid out in that order, so we can find them in dump. So, register 9, right? There's the address in register 9. Points to this lines, right? Same as. Not to fear, if I add plus 48 and get 7298 plus 48, I get the address pointed here, and if I look, it's 3TGT. If I take the 7298 and plus 12 Charlie, I'm pointed here. So this is BLW0, BLW1. Remember the COBOL compile list? BLW1 plus Charlie Echo Charlie. I'm now here. I can find my data. Register 9 plus, right, TGT plus 7298, or 7298 plus 134 puts me here. And again, we'll take a look at those, but in respect to the compile list. Okay? So I can find them in a dump. And again, I'm just going by the addresses over here on the right-hand side. So that address, right, 2801 alpha 5 alpha 0. Again, looking down the right-hand side, I'm trying to find that address, right? And essentially, it's kind of like right here. That's where it's pointing. Okay? I'm sorry. I did the plus Charlie Echo 8 and came up with the Baker 288 address. Okay? So, again, BLW1, right, alpha 5, alpha 0 plus Charlie Echo 8 ends up as Baker 288, 4 bytes packed, and you'll notice it's all binary zeros. Now, how did it get that way? Kind of why I said go look at register 14 and find the second command in the program, or the last command in the program. Because somewhere between the command and here, right, where it program checks, you did something to the data area. And that's why that register 14 of the last command is useful. I can say, oh, well, this command worked. Here's where I died. Somewhere in there, I did self-harm. Okay? When you look at the linkage section, if you don't have a DFH COM area, which my program does not, I use channels and containers, one will be there. So BLW or BLL0 is always zeros. BLL1 will be DFH COM area. Now, it doesn't show in a compile list because we use the integrated compiler. Okay? So it is there. CSS will stick in a COM area of 1 byte. Okay? So BLW1, or BLL1 rather, will be the COM area. This will be BLL2, 3, 4, 5, 6, 7, 8, and 9. Okay? That's because I have, right, 9 O1s. And then BLL10 will be the EIB. CICS inserts the integrated compiler inserts the EIB at the end. So there would actually have been 11 BLL cells because it starts with 0. Okay? We're not concerned about the storage in this particular event. So that is Enterprise COBOL 4. So let me switch gears to Enterprise COBOL 5. Going to find out it's a little different. Okay? So Enterprise COBOL 5 started building what's called program objects. So the way this kind of gets put together is a bit different. Okay? PSW is the same, right? Next sequential instruction, right? Again, second part of the full word, same. Would still be handy to get register 14 at the last command, okay? However, register 8 is the address of something called static storage for the program. Working storage, if you will, okay? This also you can see as register 8 here. Register 12, or Charlie, is the address of something called the CEE-CIA, Common Anchor Area. Remember, TGT also had that address in Enterprise COBOL 4. The Common Anchor Area, CEE Common Anchor Area, is kind of like the basis for all the LE data areas. And that's the thing. With Enterprise COBOL 5, it is now LE that's acquiring the copy of working storage for your COBOL program, not CICS. So it's LE, and the working storage is now part of the LE data within the dump. So static storage comes out of the heap. Okay, so register 12, right, points to this address, okay? And if you back up a bit, you'll see the CEE-CAA, the Common Anchor Area, okay? This CE plus, right, 1 Fox 4 is the address of something called PPA 4. When you look at a COBOL compile list for Enterprise COBOL 5, the TGT doesn't exist, but what you find is PPA 1, PPA 2, 3, and 4. 4 is actually the start of the static storage, right? It is documented in this manual called the Vendor Interfaces Manual, right? But it's documented as C++ writable static storage, and that's the actual label, if you will. But it works out for COBOL. It's just a heap, the address of the heap where the working storage is, if you will. Okay? So looking at PPA 4 in a compile list, right, you can see I've highlighted a couple addresses. The address of rent static, right? And then this address of the data 24 address minus whatever offset in static storage to working storage. So we need to find the contents of this full word in the dump, right? The rent static, and then don't worry about the data 24. My data areas are all 31 bits. That just happens to be the label it shows up, okay? But that's also going to be the offset when we start looking at the dump, right? So all right, so we got to, right, this rent static into PPA 4. It actually will be in program storage, okay? It's not something that changes program by, task by task, okay? It's just like an offset, if you will, okay? So 1, 0. Offset to working storage happens to be 0, okay? It says might expect to find 1 echo delta 0 offset, but a value at 1 delta 0 offset, but it is zeros, okay? Because again, it's an offset. So, right, I've shown you the start of working storage, my constants, and you'll notice it is at offset 0, okay, displacements, okay? And again, we get that from compile. So if I need to find a particular field, I need to know its displacement. So I don't really have like base locator working storages, base locator linkages, right? This is a whole different way of doing it. We're going to end a little early here. So once again, I get into static storage map in my COBOL list, and I find WS constants, Okay, offset into static storage where the work in storage begins. Notice 9 alpha 8. Okay, so now I can really go find it in the dump if I need to. Showed you how to pick up the addresses necessary, right, to get to the start of static storage, the 2 offsets and so on. Okay, need the program list to figure out where my first is, and again, the map is going to be +0, so it's kind of like BLW1 plus a displacement. Well, BL, in this case, the first offset is 0s, but it's going to be 9 alpha 8 from the start of static storage. And last slide. So we find the start of static storage, right, by the register. We add 9 alpha 8 to it, and that gives us the offset from the static storage to where it's going to begin. Okay, and that's kind of what I highlighted right here. Yeah, word address 8 delta 5 8 is the actual address, and I think I showed you that in the text on that page. So now I can use, let me back up a couple slides. Now I can use these displacements here, right, to find any piece of data in working storage I desire. So that actually is the last slide. I actually finished about 9 minutes early. I figured it would not take that long. Haven't seen any questions that have gone along, but if you've got any questions, by all means, please put them in the question window. Be more than happy to answer. Just a presentation to kind of pull apart the dump in a quick fashion, show you what's important, what stuff you could ignore. By no means have I taken you to the end point of solving an application of bends. That takes a bit more processing, if you will, or a bit more information. And that's what we kind of do in our application debugging class. So shameless plug, right, from my application debugging class. But I carry it to the end. And I do cover both Enterprise COBOL 4, Enterprise COBOL 5. We'll be putting up Enterprise COBOL 6, but I expect it to be similar to COBOL 5. I mean, they totally rewrote COBOL more or less, kind of, with Enterprise COBOL 5. But I expect them for 6 to keep the same basic methodology because it is program objects once again, and Ellie's doing all the heavy lifting, if you will. So I'm done.